All right, section 3.7 will conclude our chapter 3, and it is called related rates. So this is going to draw us back into something we did in chapter 2 that was perhaps a little challenging for us, called implicit differentiation. But we're going to be doing it a little bit differently. What we're going to be looking at in this section is we're going to be looking at how something is changing over time. So when we were doing implicit differentiation, we always did things with dy dx, right? Always in terms of what the variable x was doing. We're actually going to be doing everything with respect to t, time, on this one, okay? So let me show you sort of a list of steps of how this problems go. So guidelines for solving related rate problems. Often sketches are helpful, okay? Not always, but most of the time. Kind of like with the optimization problem, so drawing a simple sketch. Setting up equations of related quantities. So there's going to be equations involved, sometimes several. The third step is to differentiate implicitly both sides with respect to time, and that's very crucial with what we're doing. There will be no dy dx's. You may have a dy dt. You may have a dx dt. You may have dr dt if you're doing something with a radius, or dA dt if you're doing something with, that starts to sound like, I feel like I'm like ADD. I mean, dA dt, which is area with respect to time, or volume with respect to time. So everything is with respect to time. The fourth thing is to substitute the values for known quantities and derivatives. And then the last thing will be to solve for the remaining rate. Okay? So those are the steps in what we're doing. You also want to be aware of the things that are actually constant. That is, they flat out are not going to change. Okay? So if the height of the building is something we're talking about, the height of the building would be a constant. It's not shrinking and growing, right? But if you're talking about the length of the shadow, well, that's going to be changing with respect to the time of day we're talking about. So just because you're given a quantity doesn't mean that it's a constant or mean that it's a variable. It depends on the quantity, or it depends on the object that you're looking at, okay? So we'll see that happen actually in this very first example, so you can see the difference between the two. All right, so let's take a look at one. A fish is reeled in at a rate of 1 foot per second from a point 10 feet above the water. So this is a very good spot right here to recognize something that's constant versus something that's changing. The 10 feet above the water is not changing. The person's sitting on the boat or sitting on the pier or sitting on the shore, whatever, their height from where they're reeling in this fish isn't changing. Does that make sense, first of all? Okay. Now, what is changing is how far the fish is away from the shore. Okay, so to start with, we're going to have this 10 foot above the water level where somebody is, fishing off of or whatever. So here's our person, and they're fishing, and they've got the fishing pole out here. Okay, and I won't draw it quite like that. And there's water down here at the bottom. Water should be blue, so I'll make it blue. And they have apparently caught a fish over here somewhere. So the basic picture is, what shape do I have going on here? This is a triangle, okay? So wherever you sort of want to put the line, a fish line from, you can draw it. So if it helps you to sort of think about it from the actual edge of the straight line here instead, that's fine. Whatever it is, you know that this height, 10 feet, is a constant. And you know that what is this length right here is what's changing. And this length is changing too. I mean, we just need to know which one we care about. Okay, but when both of these are variable quantities, as we're reeling in the fish, those change. Now let's go back up and take a look at what variables we care about. So it tells us that the fish is being reeled in at a rate of 1 foot per second. So what is changing by 1 foot per second? Is it this length x, or is it the length y? By the description. X. The x is changing because that's where the fish is being reeled, right? It's the fishing line that's being reeled in. Are you guys tracking with me? That's the line. The black part right here that I've drawn at the angle, that's the fishing line. So this one right here is the part that's changing the 1 foot per second. So this right here, as a rate, you can write it as x prime if you want. It's more helpful to write it as dx dt to remind yourself this with respect to time. And it's 1 foot per second, but is that a positive one or a negative one? It's negative. Why is it negative, Edgar? Right. The length of the fishing line is decreasing, right? There's less fishing line to be had. So this is actually negative 1 feet per second. Okay, is everybody good so far? Okay. Now we're going to get to the next line. We only did the first sentence. There's a couple more sentences. It says, at what rate is the angle of elevation theta between the line and the water changing? So the line is the black diagonal we've got. The water's my blue at the bottom. And it's supposed to be that angle between them. So this is the theta that they're referencing, which is also called the angle of elevation from the water up to the shoreline. We're wanting to know how that's changing. So even though I've written down y at the bottom, has there been anything that tells me that y is going to be involved in my question? There isn't so far. Okay, so if that's the case when we're done here in a minute, I'm going to erase it, all right? So let's keep reading a little bit more. It says they wanted to know the angle of elevation, how it's changing. Okay, so how is it changing? Well, that would be d theta dt that we're going to be finding out information from, because that's a change, a rate of change. Okay. When there is a total of 25 feet of line from the end of the rod to the water, what is that telling me? X, right? That's a specific quantity for X. Now, is X always 25?
No.
No. X is not always 25. We're going to plug in 25 for X when we get to the very end of the problem, but X is not always 25. It's 25 at one moment in time, right? And then it's going to be changing at a rate of 1 foot per second, according to the information given before. There's a lot of information given so far, and I have absolutely no equations written down. Agreed? Okay. So we're at the point where we're going to create some equations, and do we all agree we don't need y at the bottom? Okay. So I'm going to erase it for this particular problem. Okay. So thinking about the quantities that I do have, the pictures that I do have with the variables and so forth, I've got a theta, I've got an x, I've got this 10 foot. How are those three quantities related to one another? Trig. That was a very good nondescript answer, but you're exactly right. It's trig. Do you remember which trig function relates them? No? Somebody help him out. What relates that? Is it cosine? Or is it sine? Or is it tangent? It's one of those three, right?
Yeah. I've narrowed it down.
You've narrowed it down to three. It is one of those three. It is its sine. And if you'll remember, the way you can, one of the ways to remember it anyway is Sohcahtoa. You guys remember Sohcahtoa? So h is the hypotenuse, and we've also obviously got the hypotenuse involved here, right? Because that's the x. So it's either the so or the ka. So it's either the sine or the cosine. And then the relationship of this 10 foot to the theta is it's the opposite side. It's not the adjacent side. So this is sine. So the relationship that I have between these quantities is that sine of theta equals what? 10. And we're going to write it down as 10 because that does not change over x, which does in fact change. Okay, now we'll plug in x as 25 later. We'll plug it in a couple of times actually. But the actual equation that relates all of these things together, no matter what x is, because it is changing, will have an x involved in it. And it might be helpful for us to write this even, because of what we're going to do in a minute, as x to the negative 1. Okay, so let's go back to our list of steps and just analyze what we've done so far. We've made a sketch. That's good. We've set up an equation relating all the relevant quantities. That's good. So step 3 says I'm going to do what? Differentiate. I need derivatives, and I'm going to do that implicitly. All right, so let's hope that I think I do, an extra blank slide. Fabulous. All right, so we're going to take derivatives. So starting with sine of theta, what is the derivative of sine theta? Cosine theta. Excellent. Oops. And then, Edgar, what did you want me to write? All right, and then we're going to have to write d theta dt. Why? Exactly. This derivative is with respect to time. Okay? So when we have things with y in it, remember how we would have dy dx? And when we did it implicitly, like if we had y squared, we'd have to do 2y and then dy dx. the same thing again, because the respect was with respect to time, with respect to x. This is now with respect to time, so we're going to have theta dt on that side. And then on the other side, what's the derivative of 10x to the negative 1?
Minus 10x to the minus 2.
Okay, good. Anything else? dx dt, indeed. Okay, so far so good? Okay. I'm going to write this just one more time to clean it up just a little bit. It doesn't clean it up a lot, but... Is that okay with everybody? All right, so I'm at the point now where I'm going to try and plug in some values, and some of these values I know, some of the values I don't know, and some of the values I know I'm supposed to be finding. So let's actually look back at what we were supposed to be finding. What is it that we're actually asked to find here? The rate for theta, right? The d theta dt is what I'm asked to be finding. It says, at what rate is the angle of elevation changing? So d theta dt is going to stay a variable. Everything else has a quantity that has to be put in, or I'm not going to be able to solve. Make sense? All right, so the first thing I need to figure out is I need to figure out what I have and what I don't have. So do I have theta? No. So I'm going to have to figure that out, right? Do I have x? Yes. What is x going to be? 25. So I've got 25 squared down here. Do I have dx dt? Yes. What is it? Negative 1. Good. So there's really only one thing I have to figure out so that I can solve this. Agreed? All right, so the d theta dt's will stay in here. That part I know. I need to find. Okay. So we need to figure out what in the world is theta in order to do this now. So let's take a look back at our picture. We know the relationship between theta and the side lengths, correct? So we have this relationship that we've got written down here that says that sine of theta equals 10 over x. But in general, while x is changing, at this specific point in time, we know the value for x. What is it? 25. Yeah. So we can actually use that information to find the value for theta at this specific point in time, which is what we need at the very end to evaluate that. So, from trig, can you tell me what you remember doing when you have an equation like this?
Take the inverse
Inverse
sine.
sine. Very good. So you're going to take the inverse sine of 10 over 25. And for the time being, we'll record this with several decimals because we're going to be using that information later on. We don't want to cut our decimal approximation too short. So let's go with at least 4, maybe 6 decimals for the moment. What do you get when you take the inverse sine of 10 over 25?
0.4115.
17 next. Okay. Is everybody good with that? You had 6 at the end instead of 7 at the end. It shouldn't hurt anything. I actually used the decimal approximation with 4 decimals when I did mine. All right, so this one's got 6 decimals. I know that that's my value for theta now. All right, it's not going to work for me. All right, so here's the cosine of 0.411517. Times d theta dt. All right, so to start with, this positive, this negative, and this negative will cancel, right? Because they're both negative. So we can take 10 divided by 25 squared. And then what? How do I find d theta dt here?
Take the inverse cosine.
Not inverse cosine.
You divide
We want to we use inverse cosine when we're trying to find an angle measure, but we have the angle measure here. So we don't need inverse cosine. We just need the normal cosine of the angle.
and then divide.
And then divide by that quantity. Right. So whatever you're getting for 10 divided by 25, you're going to have that quantity, 25 squared, excuse me. And then you're going to divide by the quantity of cosine of 0.411517. That's what that will end up working out to be. So then somebody's going to be calculating this. You're going to let me know what you get, right? several of you in.
That's 0.01745.
Did I hear you correctly? Is that what you got? Like this? Okay.
46.
4.6. Most of the time, your book doesn't have you do more than 4 decimals. So 4 decimals would probably be fine. So we can probably actually write this as 7.5 and go with 4 decimals of accuracy. That's what they tend to go with. So 0.0175. I need units on this because this is actually, you know, an application type problem that's got units in the problem. What in the world are the units that are going to be had for d theta dt? Will it be degrees?
No.
It'll be in radians. Okay. We're always going to be measuring in radians when we do calculus with things. Okay, so never degrees. And it's radians per what? Second. Why seconds? It is time. I mean, that's part of it. But why seconds as opposed to something different?
Because it was.
Yeah. It was already seconds in the problem here too, right? So that quantity will stay constant. We use seconds. And you can remember too that this is almost set up like division, right? Theta on top, the units are in radians. Time on bottom, the units are in seconds, so radians per second. Any questions on this one? Okay, let's try another one. Different picture. This is kind of like when you're doing optimization. All of the pictures that you're using, all of the examples can have different pictures, so you're going to be using different formulas based on the picture that you're being asked or being given as a description. Spherical balloon is inflated with gas at a rate of 800 cubic centimeters per minute. All right, so what's the picture I'm going to draw first? A balloon. What's it look like? Spherical. I need to draw a sphere, right? So I have the advantage of having a circle tool. And so my sphere looks pretty nice. And we'll do something like this to give it the illusion of being more than a circle, but actually a sphere. And in a sphere, the only dimension of a sphere is its radius, right? There is no other dimension. I don't have a height. I don't have a width. I don't have anything else, just a radius. Okay? That's the only dimension in a sphere. Now, it talks about it's being filled with gas at a rate of 800 cubic centimeters per minute. What is that referencing in relation to this object? Yeah, it's referencing V, which is volume, right? How do you know its volume, even if you didn't know what cubic centimeters were? How would you know its volume? Because of the cubing, right? Cubic measurement is volume. Good. So this piece right here is a measurement of dV dt. So my dV dt is 800 centimeters cubed, and this time it's actually per minute. And then the question I'm being asked is how fast is the radius of the balloon increasing when the radius is 30 centimeters? So what information does that last sentence tell me I know? What do I know? The radius. I know the value for the radius is 30. Is it always 30? No. It will be at one specific point in time, but this radius r, it actually changes, right? As the balloon is being aired up or as it's collapsing. Either way, it would be changing. So the r in my equation is actually a variable. And then what does it ask me I'm supposed to find? Yeah, how fast the radius of the balloon is increasing. And what quantity in notation is that? Some of you are saying it already. dr dt. So these are all the details that I'm sort of being told, I'm being asked to find. And now I need a relationship between all the information here. So what is the relationship between dV dt, dr dt, r, a sphere? I mean, what am I looking for? You don't have to give me the formula, but what am I looking for an equation of? Volume. I'm looking for an equation of volume. So do you guys remember the equation of volume for a sphere? It's going to have a pi r squared in it. What? 4/3. Very good. 4/3 And then you're going to have the pi r, and it's not squared though, it's cubed. It would be squared if we were doing area. So you're very close.
Question.
Yes?
Why is it 4/3?
That's the ratio that will work for it. Actually, when we take the derivative here in a moment, I want you to see something interesting that happens. It isn't an exact, but you can see something kind of cool in a moment here, okay? So this is the formula for volume. You'll see in the front and back flaps of your textbook some common volume and area formulas if you happen to need them as you're doing these. Reference those front and back flaps of your book. After I find the relationship here, I'm supposed to be finding a derivative, correct? So what would the derivative for v equals 4/3 pi r cubed be? Start with the left side. That's dv dt. And then what happens? The 3's cancel. And then I get pi r squared, and then times what? dr dt. Here's something I want to point out because you probably have never seen this before. V prime, not with implicit differentiation, but without the implicit differentiation, if we were just finding dv dr, you would find that v prime equals 4 pi r squared. Do you know what that's an equation for? What'd you find, Callie? Did you see it?
Surface area.
It's the surface area of a sphere. It is. So when you take the derivative of volume, again, not implicit differentiation with time, and that's not what I'm talking about, but I just wanted you to sort of see there's actually a relationship between the derivative of volume and the surface area of an object, and it's not just with spheres that this happens. It happens with other objects as well. Okay, kind of just that's a for free today. You got that information totally for free, not even in my notes. How cool is that? Yay. Okay, let's get back to the problem at hand then, I suppose. Okay, so over here's where we were. We've got this formula, and we've got, I think, all of the pieces of information for this one that we need. We don't have to solve for anything, right? Now, if they had not told us, they could have not told us the radius, and they could have said when the volume equals something, right? They legitimately could have said that, and then we would have had to figure out the radius. That would be another alteration of this particular problem. Whoops. So let's go ahead and use the pieces that we know then. dv dt, we actually know. What is dv dt? 800. I've got 4 pi. What is r? 30. And that's squared. And then dr dt, the only thing that we don't know, is exactly what we're trying to find. So you can find this quantity by taking 800. You can divide it by 4 pi times 900 actually, right? Because that's 30 squared. If you decide to sort of write it in here like this, be very careful with your calculator. Just a reminder here, your calculator does understand order of operations, which means that if you're entering this in the calculator, you need to enter it with a parenthesis around everything in the denominator. So 4 times pi times 900 or some variation of that, but making sure that the entire denominator is in parentheses. The other thing you can do is you could just on your regular screen type in 4 times pi times 900 and press enter, and then do 800 and divide by the previous answer, either typed out with lots of decimals or by hitting the second answer key in your calculator, which would work as well. All right, regardless of how you do it, you end up with the same answer, at least if you did it right. So what is the answer that we end up with for dr dt? 0.0707. And what are the units? Centimeters per minute? Okay, any questions on that one? Did everybody have that quantity? Work out okay in your calculator? All right, great. We have one more example, and this example does a couple of things for us that the other ones haven't, which is why I wanted to bring it in. One of the things that it does is if you take a look at there, We're just going to read through it at face value first, and I want you to be aware of something happening. Oil spills out of a tanker at a rate of 90 gallons per minute. The oil spreads out in a circle with thickness 1/8 inch. Determine the rate at which the radius of the spill is increasing when the radius reaches 100 feet. So somebody tell me something they're seeing happen here that we didn't have happen before. There's at least a couple of things you could mention.
Like if you have height.
There's a height. I didn't think about that being sort of different, but that's true. There is a height involved.
Your area and your volume are both changing.
The area, when you mean like the area, like the surface area of it, but that happens on the other shape as well.
But it's two of them. It's the area and the volume.
But the area and the volume changes for the sphere as well as it increases and closes. So that's not actually different. It's doing it for a different shape. That's true. There's something else going on here that's weird. You guys haven't picked up on just yet. What does this mean? Inches. And what does this say?
Feet.
We're going to have to make amends for that, aren't we? I can't do the problem with inches and feet in the same problem. So I've either got to turn everything into feet or everything into inches. That's a problem. I mean, a legitimate concern. We've got to fix that issue. We can't just put in the 1/8 and put in the 100 and just see what happens. We will be mixing up units. That doesn't work. There's something else that's weird, and you probably don't have the information just in your storehouse. I don't have it in mine to know what to deal with. This says 90 gallons per minute. And that doesn't relate to inches or feet as it's currently stated, does it? No. And so one of the things that's actually given in your textbook when they first introduced this problem, which is in an example, is they give you the rate to actually convert this into the feet units instead. Okay? So they actually tell you one more piece of information, and you'll need this for your homework because I've given you one problem that's similar to this. Where did I write it down? Oh, 1 cubic foot is equal to 7.5 gallons. So we're going to need that conversion. We also need the conversion somewhere in the framework here that 1 foot is equal to 12 inches. I know you guys know that, but we're going to have to use that in either turning everything into inches or everything into feet, one or the other. So those are both sort of, if not prior knowledge, at least extra knowledge that's not actually given inside of the problem that we're going to need. So if I were giving you this particular problem on the test, I would tell you that 1 cubic foot is equal to 7.5 gallons. But I'm probably not going to tell you that 12 inches is equal to 1 foot. I think that's probably one you remember, okay? So, all right. So we're going to need this sort of as extra information. First, though, let's actually draw a picture. What is the picture of this image? You mentioned something about height, Edgar. What is the picture of the image that we have as this oil is spilling out? It spills in a circle. Okay, so we've got a circle, but is it just a circle?
No. Yes. I mean, it's like a cylinder.
It's actually a cylinder. It's a circle with thickness. Now, it's not very thick. I mean, 1/8 of an inch is not very thick. But that's what they're describing. It has thickness to it. And since it has thickness, the shape's actually a cylinder that it's spilling out into. You guys tracking that okay? So I would encourage you to sort of exaggerate the dimensions of your cylinder because it's going to be easier for you to draw and to look at if you do. And you've got this cylinder now instead. Now, the height of the cylinder, as we've mentioned a couple of times, is 1/8 of an inch. Is that constant or is that a variable? That's a constant. So what happens as this oil tanker spills out the oil is that it is a constant thickness to it. Any liquid has a thickness to it. If it's going to be a standing liquid, there is going to be a thickness. I mean, it doesn't disappear into nothing, otherwise it would just dry up. Right? I mean, that's kind of the whole point. So there is a thickness to this. It doesn't dissipate any further than 1/8 of an inch is what we're sort of being told. All right, so let you make the decision. Do you want to put everything in inches or do you want to put everything in feet?
Inches.
Inches? Everybody agree? Okay. If you choose to put it in feet, you'll have a different answer, but it'll because your units are different at the end. So I've got it worked out both ways, so we could do it either direction and we can make sure. But we can do it into inches. That'll work. So 1/8 of an inch, and as a decimal, we could use it as decimals if you want, which would be 0.125 inches. Or you can leave it as 1/8. That's fine as well. But this is the value for the height. They give you a couple of things. They tell you the radius is obviously important with what's going on here. And at some point in time, we know that the radius has a value of what?
100 meters.
Yeah, 100 feet. But 100 feet isn't good if we wanted to turn everything into inches. So what would we have to do to feet to get it into inches?
Multiply by 12.
Right, and one of the ways that I always talk about changing feet and inches around is to set this up as a multiplication, like a ratio. I'm going to put feet on bottom, and I'm going to put the inches on top. And the reason is because then the feet cancel, leaving me with inches. Every now and then, not because you're not thinking, but just because you think backwards about something, you'll end up multiplying or dividing instead of the other. You'll just do the wrong operation. So if you set it up like this is actually called dimensional analysis, then you don't have the ability to sort of mess it up because you've got things to cancel out. So we will, in fact, multiply by 12, you're right. And so if I take 100 times 12, what do I get? 1,200. So this is going to be 1,200 inches. The other thing that I'm being told is I'm being told that it spills out at a rate of 90 gallons per minute. Well, none of the other measurements, of course, are in gallons. They're in inches now. So we've got to convert this, all in all, at the very end, into inches. The ratio that I'm being given is actually a conversion into feet, though, so I'm going to have to start there, right? So I've got gallons on bottom, because I want the gallons to cancel out, and it's 7.5 gallons is going to be 1 cubic foot. So the gallons will cancel. Now, there's more to it, though, because I'm wanting to put things into inches, because that's the decision that we had made, right? So if I need to turn this into inches, what am I going to have to do to turn cubic feet into cubic inches?
12 for 1, that's 3 times.
Right. I'm going to have to do feet on bottom, inches on top. But in order to get it cubed, I'm going to have to do it cubed. I mean, like, I need cubic feet on bottom, not just feet, right? So this is 1 foot cubed. This is 12 inches cubed. So it isn't just that I'm going to get inches cubed, I'm also going to get the 12 cubed, right? 12 times 12 times 12 in order to make that happen. So let me actually use the next slide to see this. So we actually end up with taking 90 times 1 over 7.5 times 12 times 12 times 12 over 1. Or you can think we've got 90 times 12 cubed over 7.5. What is this number value that we get for this?
20,736.
So I think you mean 20,000, right? Okay. 20,736. What are my units?
Inches per minute.
Good. Cubic inches per minute. What is this quantity that I'm finding? I mean, what's its name? What is its, when in the context of the problem, what is it? It's volume. You know it's volume because it's cubed, right? But it's not just volume, it's dV dt, because it's the change in volume over time, over the minutes, agreed? So we've got volume over minutes, so dV dt. Okay. The reality is we haven't done any calculus yet. Do you guys recognize that at this point? All we've done is conversions. So we are actually still on step 3. We need to actually step 1. We haven't even created an equation yet, actually. We need an equation relating this shape with this information. So what is the relationship that we need here? What is the quantity that's being involved? Volume. All right, so we need to talk about what is the volume formula for a cylinder.
A squared pi.
Right, it's the area of a circle, pi r squared, times h, the height of the cylinder. Is everybody good with that? Okay. Please recognize the height in this situation is a constant, right? It's not changing. So I really don't have two variables on the right-hand side of this equation. I really only have the variable r. H is not a variable, so there is no dH dt here. Doesn't make any sense because it's not changing. That's important to realize because that's an easy way to get confused because it looks like there's two letters, right? We just want to recognize that those letters are not both variables. All right, so I need a derivative. What's the derivative of the v? Right. And then I need the derivative of pi r squared h. 2 pi r h, because it's a constant, right? It just gets to be there for free. And I need dr dt. I do. Right? Because r is the variable. Again, there's no dh dt because h is not a variable. It is a constant. And if it helps you, you could actually plug this in here at the beginning. You could actually put the 1.8 in right here and just go with it. Not 1.8, 1/8 in and just go with it from there too. So at this point, I tend to wait till the very end and then put all the values in those. So that's kind of the route that I'd go with. We know dv dt. In fact, we solved it up earlier on this same slide. That's the 207/36. I've got 2 pi. What is r? That's the 1200, right? What is h? 0.125, or 1/8 if you left it as a fraction. And then dr dt, it's fine that we don't know it because that's actually what we're looking for, right? Awesome. So then, take a moment, multiply things out, divide them, and so forth. You will have dr dt equal to the 207/36 divided by 2 pi times 1200 times 0.125. It would look something like this if you wanted to put it in your calculator straight away. What's that give you? 22, and it's almost exact, isn't it? Yeah. If I remember right, it had like 2 zeros after it, didn't it? 0015. So I think 22 is reasonable for us to just leave it at 22 on this particular one since it's 0.00. 22 what? Inches per minute, that's right. The radius r currently, we let that be in inches, and the time was in minutes all the way along. Now, be aware, let's say, for instance, you did this problem and you got this answer, but then when you flip to the back of the book, they didn't do it in inches, they did it in feet. So your numbers, of course, don't match. What could you do to just, you wouldn't need to rework the problem, but what could you do to check your answer to see that you did it right? Yeah, you just turn it into feet, right? So in this case, you would take the 22 and do what with it? Divide by 12, exactly. So I don't want you to think that you have to do it in the unit necessarily that they do it in. That is not appropriate at all. You can choose the unit in the case like this. It's just that the answers wouldn't match at the end because the units wouldn't match at the end. Okay? Any questions on that one? All right.